Hello everyone and welcome back. My name is Mr. Koval, and in this video we're going to show you how to describe this molecule based on valence bond theory and molecular orbital theory. So let's get into this. Okay, so this problem is a long one. It says given the molecule C6H5C CHCH2, draw the Lewis dot structure of the molecule. The connectivity is indicated by the order of atoms. Draw the skeleton of the molecule using valence bond theory or VB theory, or also that's what we that's the theory that uses hybridization like sp2, sp3, sp3d, and all that stuff. Show all the unhybridized p orbitals. Would this molecule be a good candidate for molecular orbital theory? Why or why not? And how many molecular orbitals would this whole molecule have? Okay, that was a mouthful. Okay, let's do this step by step. So first, the Lewis dot structure, it's indicated by the conductivity. So whenever you see this part here, C6H5 or C6H6, that indicates a benzene ring. Okay, so that means you're going to have 6 carbons bonded together in a ring. And you'll notice that then you have the 5 hydrogens connected, 1 to each carbon in the ring. That's where the 5 hydrogens come in. And then the rest of it is bonded off of one of the carbons. So you'll see this carbon is then attached to one of the carbons here. And then this oxygen is bonded to the carbon. And so you have that oxygen there, that would be the oxygen here. So this carbon is bonded there, so we have that carbon bonded here, oxygen bonded there, and then you have this CH group right there, so CH, so this bond there, and then the CH2, this right here, and there's a double bond right there. And so this is the Lewis dot structure. Now, there's another way, depending on how we understand that oxygen. I understood it as a ketone, but it could be the case that this oxygen is bonded directly between the 2 carbons. So everything else would look the same. So if I draw just a sketch of what this molecule looks like. Okay, so there's the 6 carbon ring. I'll put a circle there because the benzene ring is usually written that way. Oh gosh, that looks ugly. Let me do this again. So like that. Oh, that's much better. So here's your 6-membered ring. Each corner is a carbon, and then there's 1 hydrogen on there. Sometimes we don't draw the hydrogens. And then this would be here. So there's your carbon. And then instead of the oxygen being there, it would be bonded between these 2 carbons here. So bonded, you have the oxygen there. And then you'd have that carbon there. You'd have 2 lone pairs on the oxygen, like so. And then you'd have a double bond between the carbons there and the 2 hydrogens. And now here, you'd have to figure out like what's going on with the carbon here, because in our molecule, there's no hydrogens on this carbon. It's just the carbon bonded to the oxygen. And so maybe there's a double bond here, and then there would have to be a double bond here as well. So this one doesn't really work that well. So this couldn't be the structure if that's what you're thinking. If you're thinking it's some kind of ether, so then this would not be the right one. So this seems like the correct structure. It's a ketone. If you have a carbon double bond oxygen, and this is called the carbonyl group. If that's bonded to two carbons, that's called a ketone, just FYI. Okay, so here's the Lewis dot structure of this molecule. And so now we're asked, so that's, then we're asked, draw the skeleton of the molecule using valence bond theory. So valence bond theory basically says that we're going to hybridize our atoms. We're going to take our atomic orbitals on a particular atom, hybridize those together, and we'll spit out equal energy hybrid orbitals on that atom. This is a localized model, so the electrons stay with the atom. So here's what it would look like according to the valence bond theory. And so we could use valence bond theory to show the sigma bonding, and then molecular orbital theory could show the pi bonding if there's resonance, right? So you could see that from each carbon on here, you have 3 electron groups. Double bonds count as 1 electron group. So because each carbon has 3 electron groups, that indicates that you're going to need 3 atomic orbitals that are going to be hybridized. So you're going to be an S, you're going to need an S, a P, and a P. So that's sp2 hybridized. Anything that's sp2 hybridized is going to be trigonal planar. So all of these are trigonal planar around the carbon. So you can kind of see the triangle, and they're all in the same plane. So if these are all sp2 hybridized, so that means that there's going to be like a 120-degree angle here. This is all in the same plane. And you can see that these are all sigma bonds. So we have, this is not an oxygen. This is the s orbital for the hydrogen. So you can see that the s orbital for the hydrogen has 1 electron in there. And then each of the sp2 hybrid orbitals has 1 electron. So valence bond theory is where basically you're taking single electrons from orbitals from different atoms, and you pair them up and you form a bond. So we have a sigma bond here between this hydrogen and the carbon. And so we see that right here. So that's that bond there. This bond here is represented by the overlap of the orbitals here. Again, sp2 hybrid orbital with an unhybridized s orbital of the hydrogen. They both have electrons, spin down, spin up. And you can see along the carbon, you can see between these two carbons, you have an sp hybrid orbital overlapping with an sp2 hybrid orbital overlapping with an sp2 hybrid orbital of the adjacent carbon. So you're forming a bond here. So this is what this bond is. And so you could see the overlap of the orbitals forming the bonds. So spin up, spin down, you got 2 electrons there. Hydrogen with the s orbital overlapping with the sp2 hybrid orbital of this carbon forming a sigma bond. So you have 1 electron spin down, 1 electron spin up. And so this showing the sigma bonds of the carbons in the ring with each other, as well as the sigma bonds with the hydrogens, so shown here. And you've got the bond here, a sigma bond, so between these two carbons. You've got a sigma bond between the oxygen and the carbon here. And you've got these sigma bonds. So this bond here, this bond right there, this bond between the hydrogen and carbon right there. Here you have a sigma bond, Here you have a sigma bond with the double bond, right? So we're ignoring all the pi bonds and just focused on these sigma bonds. So this shows the sigma structure of the molecule using valence bond theory hybridization. Now, since these are all sp2 hybridized, every single carbon on this atom and the oxygen are sp2 hybridized, which means that every atom except for hydrogen has an unhybridized p orbital. So remember, you have to form sp2 hybridization, you take one s and two p's. Well, you have three p orbitals. If you take two of them for the hybridization, then that leaves one unhybrid orbital. And since all the atoms except for hydrogen in the molecule are sp2 hybridized, that means every single atom except for hydrogen has an unpaired, unhybridized p orbital. Now, where are those p orbitals? I can't draw them, even though it's asking you to show all the unhybridized p orbitals. My artistic abilities are just not that good. But what I can say is basically this is a completely planar molecule since they're all sp2 hybridized. That means that they're all trigonal planar. So all of these atoms lie in the same plane, which means that the unhybridized p orbital, which in this case, typically the pz orbital, is going to be perpendicular to the plane. So that means that it is perpendicular to the plane of this whiteboard here. So this molecule is in the plane of the whiteboard, which means that the unhybridized p orbitals of all of the carbons and oxygen are coming out of the board and going into the board. So kind of like this. So if this is my p orbital, then at the center of this carbon is going to be a p orbital sticking out of the board and into the board. This carbon has an unhybridized p orbital. This carbon has an unhybridized p orbital. This one has an unhybridized p orbital, and so on. So every atom, even this oxygen here, has an unhybridized p orbital. So the system of the p orbital looks like this. So every atom has a p orbital sticking out of the board and going into the board perpendicular to the board like this marker. So now if we think about delocalization of the electrons and pi bonds and things like that, each of the unhybridized p orbitals is going to have an electron in it. Those electrons are delocalized, which means that those p orbitals can interact to form molecular orbitals. Now we're using molecular orbital theory, right? So what happens with molecular orbital theory is that all of the unhybridized p orbitals can combine together to give molecular orbitals. And as we know from previous videos, the number of atomic orbitals that you are using to make your molecular orbitals gives you the same number of molecular orbitals. So if I am using 5 atomic orbitals to create molecular orbitals, then I'm going to produce 5 molecular orbitals. And so again, if I have 7 atomic orbitals that are being combined together to form molecular orbitals, then I'm going to get 7 molecular orbitals, right? So whatever number of atomic orbitals I'm using to combine and get my molecular orbitals, I'm going to get that same number of molecular orbitals out from those atomic orbitals. So that is going to create on the outside, on this side of the board, I'm going to have an electron density. So here, I'm going to have an electron density from the interaction of the unhybridized p orbitals here. I'm going to get a donut-shaped density on the top here above the ring on this side of the board. And because the p orbital is on the inside of the board as well, going this way. Below the ring, or on the other side of the ring, I'm going to have another donut below this ring. So I'm going to have a donut on this side. I'm going to have donut on the other opposite side of the ring. Same thing here. I have unhybridized p orbitals here and here and here on top on this side of the board. So I'm going to have electron density following the chain here along this bond and along these bonds here, forming electron density on this side of the board. And behind the board, below the chain, I'm going to have electron density. So I'm going to have electron density on this side, I'm going to have electron density on the other side, because all the p orbitals are interacting with each other to have that electron density. Now, again, I'm not showing it because, again, my artistic abilities are not that good, but I'm hoping my explanation is clear enough. Now, based on what I said, we can answer a couple of questions. It says, would this molecule be a good candidate for molecular orbital theory? The answer is yes, it would. And why? Because it has resonance. So you can see here, as I can show here, these bonds, you can move these bonds around, right? So this carbon bond can move here. This this double bond can move there. This double bond can move there, or it could also move here, right, creating a double bond there, which would push the electrons from the double bond here, right? That would create a single bond here and 3 lone pairs on the oxygen, right? Or instead of going here, it could go there, but then the double bond here, right, could be pushed up because this bond here, how do I want to do this? So this could be pushed here, up there, and also this bond might move there and then push that up there, so you can have a double bond there and a single bond here, right? So that means that this would have a positive charge on it, right? So you can move electrons all around. So there's a lot of resonance in this structure. And so one thing to remember is if your molecule has any resonance in it, or if you can draw resonance structures for the molecule, then that means that's a good candidate for molecular orbital theory. Why? Because we can use molecular orbital theory to explain the pi bonding without having to refer to resonance structures. So that's the answer to that question. And then finally, how many molecular orbitals would this molecule have? Well, if we're, again, as I said before, whatever the number of unhybridized p orbitals that are going to be involved in the formation of molecular orbitals, that's going to be the number of molecular orbitals. So let's look at our molecule. Okay, so let's count here. So I think I misspoke here. That's actually not, we wouldn't get this movement here. So that double bond is going to be pretty much staying there. However, this double bond can move between there as well. It's not going to move here because, again, this carbon, this is really not going to happen. So how do we count the number of unhybridized p orbitals? Well, this is sp2 hybridized here. So there's an unhybridized orbital here, and every carbon in this ring has an unhybridized p orbital. So that's 6 p orbitals. And so that's going to be 6 molecular orbitals there because we have 6 atomic orbitals in this system here. And then you've got a double bond there. That's going to involve an unhybridized p orbital on your oxygen and unhybridized p orbital on this carbon here. So that's two unhybridized p orbitals. So that's another two molecular orbitals. So that's going to be 6 plus 2 is 8. And then we have a double bond here. That's going to involve two unhybridized p orbitals. So that's two atomic orbitals. So that's another two molecular orbitals. So 8 and 2 is 10. So the whole molecule is going to involve a total of 10 molecular orbitals because we have a total of 10 unhybridized p orbitals involved in pi bonding. And that, ladies and gentlemen, is how you answer those questions. Just to reiterate, so here we're not, this system here can be tied to here, but we're not going to get a double bond forming there, as I think I mentioned. So this double bond isn't really going to be connected with the rest of the system, but still you can count the unhybridized p orbitals in order to figure out how many molecular orbitals you have. That's it for the video. I hope you enjoyed the video. If this helped you in any way, if you enjoyed the video in any way, then please, by all means, like the video, share the video, hit that like button somewhere. Also, make sure you subscribe to my channel. Help me out, please. I beg you. When you do that, make sure you click the notification bell and click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. I'm begging you. I would love to hear from you. If you have a question or a problem you need help with, or if you have a topic you would like me to cover, I would love to do that for you. Just let me know. Thanks for joining me and have a great day.